So let's say we run k-means on our data set with a value of k equal to 4. So we're going to start out with 4 centers that'll be randomly placed, and then k-means will run until it converges and we reach a stable result. So let's say this is the output we get when we get that stable result. So if we were to run k-means all over again, we would get a different output. And so here are 3 runs of k-means where we ran it until we reached a stable solution. And the first one was done with a random seed of 25, the second with a random seed of 29, and the third with a random seed of 40. So we could ask the question, which one of these is best? So to answer that question, one approach would be that we define some form of loss function. And we've seen this over and over in this class where we have to come up with a loss function. So it was L1, L2 loss for regression. It was cross entropy loss for classification. And when we looked at decision trees, it was weighted entropy as our loss function. So your challenge is to take a moment, pause the video, and try and come up with what would be a loss function that we could use for our clustering output. Okay, so one idea might be the sum of the distances from each point to its center. Another one would be to look at the balance of what are the number of points in each cluster and see do we end up with a good balance of points per cluster. So these are just examples of what we might use as loss functions. And let's look at what are actually commonly used as loss functions. So 2 commonly used loss functions are inertia and distortion. Inertia is just the sum of the square distances from each data point to its center, while distortion is the weighted sum of the square distances from each data point to its center. So here we have an example where we have 7 data points, the 3 data points in blue and the 4 data points in yellow. And then the stars represent the centers of those clusters. So we don't count them as data points. Okay, so inertia is just going to be, we'll sum up the squared distances from each data point to its center. So the lower left-hand point is 0.47 from its center. So it'll be 0.47 squared. The one just above that is 0.19, so it'll be 0.19 squared. And the one below that is 0.34, and so it'll be that squared. And similarly, we'll do the same thing for the distances of 0.25, 0.58, 0.36, and 0.44 for the yellow points. And then when we sum all of that up, that gives us our inertia measurement. Distortion is slightly different. We're going to weight that sum by the size of the cluster. So in this case, for the blue cluster, we'll divide by the size of that cluster, which is 3 data points. And in the case of the yellow cluster, we'll divide it by 4, since that's the number of points in the yellow cluster. So which you use, some people use distortion, some people use inertia. Scikit-learn uses inertia, and so that's what we're going to use in this lecture. Okay, so here are the inertia values for those 3 runs of k-means. So on the left, we have an inertia value of 44.96. In the middle, we have an inertia value of 45.95. And for the rightmost graph, we have an inertia value of 54.35. So looking at this, this tells us that our loss function tells us that the leftmost clustering is best. It has the lowest inertia. And the rightmost clustering has the highest inertia, so it would be the worst result. So it turns out that what k-means is trying to do is minimize inertia. But it's often going to fail to find the global optimum. It might find a local minimum instead of the global optimum. So why is that? Well, let's do a sort of a quick sketch of what k-means is doing. So what you can think of k-means as doing is that it's a pair of optimizers, and these optimizers are taking turns. So you have one optimizer, the first optimizer, that holds the center positions constant and then tries to optimize the colors of the data points around those centers. And then you have the second optimizer, which at the same time holds the data colors constant and is trying to optimize the center positions. And so neither gets total control, and so neither is going to be able to find the global minimum all of the times. Sometimes you will find a global minimum, but many times you'll find a local minimum instead. So this is a really hard problem, right? To give an algorithm that optimizes the inertia. And so that's the challenge to you. Come up with an algorithm that optimizes the inertia. And your algorithm should give the exact best centers and colors. Don't worry about the runtime. And this is really kind of a very, whatever, CS61B, CS70, CS170 type of problem. And so for some of you, I know it's going to be too hard of a problem if you haven't taken a theory class already. So take a moment, stop the video, and think about what your algorithm would look like if we want to get an exact solution. Okay, so here is an algorithm that we could use, and it works as follows. We're going to generate all possible k to the n colorings. And a coloring is just a choice of color for every point. So we could say point 1 is red, point 2 is green, point 3 is red, point 4 is blue. And we're going to do all possible colorings. And then for each one of those sets, from that set of all possible colorings, we're going to pick a set. We're going to compute the k centers for that coloring. And then we'll compute the inertia that's associated with those k centers. If the current inertia is better than the best known inertia, then we'll write down the current centers and coloring, and then we'll call that the best known selection. So if we do that for all k to the n possible colorings, that is the best that we can do. There's no better algorithm, and this is going to have exponential running time. And so what that means is, k-means is an NP-hard problem. So if you could find an algorithm that was better than this algorithm, you would become world famous because you would have found a solution to an NP-hard problem. So this is the best we can do. Oftentimes what we'll do instead is some approximation. And because we're doing an approximation, and that's mainly in the interest of running time, because the time to actually compute all k to the n possible colorings could be very significant if we have a large number of points. So we'll often use an algorithm that does an approximation, which means we may end up with a local minima and not the global minimum.